Hello everyone, welcome back to ECE410 Power Electronics, class number 10, lecture part video number 3. All right. In this part, we're going to talk about discontinuous conduction mode. The first part we talked about buck boost converter, and second part we talked about the critical conditions. Now we're going to talk about discontinuous conduction mode. As we said before, discontinuous conduction mode has a period of the time of the period when none of the switches are off, and also there's no current. So this is the period right here where current IL is 0 and switch 1 and 2 both are off. So if we separate them again, as we did before, this is the input current over here, and this is the output current. So after the output current, there's an off period right here, okay? So now, how do we analyze this? How do you find the relation between input and output voltage? So this is the input current here. If you're trying to find the average input current out of this, we have to integrate that over time, right? So if you integrate it over time, it's a triangle, right? We'll get the area under I in. This is the I in here. This is let me get a different color here. So this is not that one. Let's get a green color. So this is your I in here. So if I integrate that, I'll get the area under that curve. That is basically right here, right? And for the output current, same way, if I integrate that, I'm going to area under that curve over here. That is right here, all right? So problem is that we don't know D2 because D2 is not known because D1 plus D2 is not 1 anymore, right? So we don't know the D2. But we can still use the equation for D1 because we know D1. So VL L di dt, right? And you also know that for this condition over here, your peak current is basically your peak-to-peak ripple. Peak current is your peak-to-peak ripple, right? So if you can incorporate that into this equation over here, we'll get that peak current is this, because peak current is your peak-to-peak ripple, right? And from there, now we can also find the input power, which is V in times I in average, and your I in average right here is basically this, right? And I know this guy from here, right? So we can incorporate this one here, and this equation over here. We'll get this. This is your input power. For the input power over here, you know that V in squared D1 squared over 2 times T by L. So that's your input power. It's right here. So this is your input power in discontinuous conduction mode. But if we think about that lossless converter, so input power should be equal to output power. And what is the output power? Output power you can easily get if on the output voltage squared over R. R is the load there, right? So now if we equate these two equations now, this one and this one over here, this is your equation, right? So from there, your V out would be this one with the polarity inversion, right? So look at here. The first problem is that before your buck boost converter, V out was negative D, 1 minus D, V in, right? So there is no R or L or T in there. It's just the D ratio, right? So you can have a very predictable relationship between input and output. But here, your output depends on D ratio as well as your input voltage, but it also has R, T, and L. So that means if anything changes, then your output changes. So output becomes not predictable for discontinuous conduction mode. So this is the relation with this one, discontinuous conduction mode here. So the relation is for buck boost converter here. This is the relation for buck converter. This is the relation for boost converter. So all this relationship is not linear anymore, as well as I would not say linear. It's not predictable anymore. You have R, L, and T into the equation, so it makes more complicated dependency between input and output. So output magnitude is higher with a larger L, and you have other relationship in there. So still your energy conversion it still holds there, right? And but your relationship between input and output becomes more complicated. So does it matter? problem is that at light load, right, if you design the converter to supply, let's say 100 watt, at some point if your converter is supplying only 5 watt, it's very likely that you're going to go into the discontinuous conduction mode. If 5 watt, you have light load. At light load, your inductor current will be small enough to make have a zero current at some point. So at light load, you might get into the discontinuous conduction mode. One of the things is that for discontinuous conduction mode, very fast response because you're not storing any energy into the inductor, and very small value of L, so you can go with a very small value of L, and you have extra output voltage if it's necessary, like useful for your purpose. And disadvantage, your output voltage does not only depend on D ratio, that also depends on R, L, and also T. You're switching very fast, right? Current variation is really high because you're swinging up and down, very high value of current, very high ripple. You might get into magnetic saturation. And it's not easy to keep the output voltage constant because it doesn't only depend on D ratio, but also depend on R, T, and L. So those are the disadvantages for DCM, discontinuous conduction mode. So as I said, light load, right? If you have a converter designed for 100 ohms, 100 watts, and if you're supplying 5 watt, it's very likely that you're going to get into the discontinuous conduction mode. So how to avoid this discontinuous conduction mode? One way of doing it, if you design a parasitic load, always connected to the inverter when it's on, and that parasitic load will make sure that your converter is in continuous conduction mode all the time. So what it means that, let's say you have a converter here. Let's look at your buck boost converter, which is this. So let's say this is the load we have always be connected. It's called RB. So that is always connected to the converter, no matter what you have, load or not. So you have the load over here. So the load will come later, right? So what will happen? For this one here, for RB, if this is not connected, there's a current here. Like let's call it ILB, right? So that would come from this one. So this ILB would be like this. So your ILB will be like this, right? So this is your ILB due to the load right here, due to this load over here, right? So now if we add another load to the this is the converter itself, right? Now if I bring the load here, what will happen? This load and this load, your load impedance will go down, your IL will go up, right? So IL go up, then you're gonna bring this to somewhere here, right? So that means you're basically going to the normal operation for the inductor, right? So that's how you can avoid your converter going into discontinuous conduction mode when you have a parasitic load to the converter all the time connected that assures this critical operation. And if you add more load, your inductor current goes up, so you go into the normal operation. So that kind of load is called ballast load. How to design one for the ballast load? We're going to get them into the class when we solve the problem. All right. Until then, this is all for this class 10. Then we're going to get to the class 11 in the next video.